Yeah, yeah, absolutely. So I met Don while working at HP quite a few years ago when I was there, and I mean, for lack of a better word, Don is one of the smartest people I know when it comes to any type of assessment. So I'm really looking forward to her talking today. My tenure with Don was mostly mobile application security, and I know that she's still in that world where I have kind of fallen off a little bit. And I had talked to her recently, and I said, like, do you have anything cool that you've been doing? And just her experience with Frida and getting into it, and the functions and stuff to use it for seemed like a great opportunity to have her come talk to the people at BugCrowd who were doing mobile stuff. So I'm really excited for this talk personally. Dawn is a great human, epic hacker, and yeah, I'm really excited to have you here, Dawn. Thanks for coming by.
Thank you. Boy, what an introduction. And it's on a recording now that I'm the smartest person you know. So
Yeah, there you go. And everybody else feel bad. It'll be great.
yeah, I'm going to put a pin in that one. Well, I'm really glad to hear you're excited about the talk because I am very excited to be here today because this talk is really talking about one of the tools that I enjoy using the most when I'm looking for bugs in mobile applications, and that's Frida. So my goal today for this talk was really to gather all the basic knowledge in one place that I think folks need to really hit the ground running with Frida. And hopefully what you get out of the talk is just enough information to make your bug hunting on mobile both more efficient and a heck of a lot more fun. Oh, and unfortunately here, hang on, I'm having some technical difficulties. All right, there we go. So first, let's talk about motivation, though. From my perspective, looking at black box mobile application testing, there's some challenges that we encounter when you don't have source code. Now, obviously, if you're looking at Android, you can address that somewhat by decompiling to source, although you might run into obfuscation or some other issues that prevent you from fully understanding what's going on. But on iOS, we don't really even have that option of decompiling to source. So we have some limitations right off the bat in digging into complex applications and understanding exactly how they work. Depending on your environment, you also might have very limited debugging capabilities, especially on a non-rooted or a jailed device. You might not have very much access to the environment that the application is running in either. So there's a lot of things you have to surmount with black box testing in order to really get a good feel for what the application's doing under the hood, especially if some of that functionality isn't manifesting in a visual way in the interface. So this is where I feel like Frida addresses a lot of these gaps very well. Frida's a framework for dynamic instrumentation. And in practical sense, what that means is that you can actually inject your own JavaScript into an application at runtime and execute it from the context of the application. So your code can see what the application sees, it can do what the application does, and that can be a very powerful tool for understanding exactly how that application works. Frida also provides a really nice API so that you can build custom tools. You're not just limited to the tools that Frida provides out of the box, but you can build your own tools that are very lightweight and portable and can address very specific use cases within the application that you're testing right this minute. So one of the nice features of Frida that I think contrasts with a lot of mobile tools and frameworks out there is it doesn't necessarily rely on you having a jailbroken or rooted device, although that is kind of the easier way of working with it. If you do have that type of device, there's an injected mode for Frida where it just runs in a server on the device that your client scripts can talk to. But if you're stuck with just working on a stock device, it also has an embedded mode where you can either repackage the application basically with a Frida gadget shared library that can do a lot of the same things that Frida server does. It can listen for connections and also has some other nice features that you can customize if that's what you're working with. Now, I'm not going to really go into using Frida gadget here. There's a lot of great write-ups and blog posts out on the internet that you can find that goes step by step through it. It can be kind of a complex process depending on what you're working with. So most of the examples we're going to talk about today were performed in injected mode, but a lot of them would still be perfectly usable if you were running in embedded mode as well. So Frida's toolkit right out of the box comes with some very usable tools that honestly, even though I've written some of my own tools, I still use these on a daily basis. And really, this is where I recommend people start if they've never seen or interacted with Frida before. Frida Trace and the Frida command line interface. And we'll see a lot of examples throughout this talk of how to use both of these. Frida also provides bindings for a few different languages. So if you have a favorite scripting language, say that you really like Python or you're very comfortable working in .NET, there are bindings for these so that you can create your own tools in that environment that you're already familiar with and comfortable with. So let's just start by diving into a very simple example of using Frida Trace on iOS. What Frida Trace does is logs functions and method invocations at runtime that we can specify. So in this example, I'm targeting Objective-C methods in an iOS application using the -m flag. And I can provide a pattern using an asterisk as a wildcard to match on just simple patterns of things that I'm looking for. So as an example, let's say you have an iOS application that's really resisting your efforts to push the traffic through a proxy. Maybe the application doesn't obey the system-wide proxy settings, or you're having some other technical difficulties and you just cannot get to that traffic that you need to analyze the application. So you decide, well, I'm going to use Frida and just trace some of those network calls on my own. And I'll start with NSURL request in it with URL cache policy timeout interval, because that will show me the URLs that the application is constructing in these requests. So if we wanted to just trace that particular call, we could use this command line at the bottom, Frida trace -u, which tells Frida that we are operating with a connected device over USB. So it's going to send all of its calls over USB. -m says this is the pattern of Objective-C methods that I'm looking for. And in our case, we just want to trace instance methods. That's the minus. If it was a static or class method, we could put plus or an asterisk if we don't care. We want either one. We want just NSURL request methods, and we want the method to match init with URL :cache, and that's basically our prefix. Anything that matches that prefix will be returned in the trace. And then we'll specify the name of the process, our application's process, after that. So if we were to execute this against the Apple News application on a device, we would see something like this. First of all, Frida has told us it has found exactly one function to trace, which is great. We don't have a lot of garbage we have to wade through because we've targeted exactly what we're looking for. And then you can see a really nice color-coded output. And this color coding denotes the different threads that are active within the application. And it might not be real obvious here since we're only tracing one function, but if you had a lot of functions that you were tracing, it can be very nice to see which threads are calling which function and how those threads are ordered or nested, or how I should say how the actual calls are ordered or nested on that particular thread. So we do see that we have invocations of init with URL cache policy timeout interval. But beyond that, it's not really telling us a lot. We don't see what the URLs are. We just kind of see a pointer. So we know there's something there, but there's not a human readable representation of it on the screen that's going to help us out. But we can make that happen. So Frida Trace generates what it calls handlers for each method that it finds. And these are just auto-generated JavaScript stubs for code that's invoked both before and after each method call that you're tracing. And we can modify these. Frida will actually tell us exactly where these handlers are located. You can see in the snippet that I've excerpted from the trace at the bottom here, it gives the exact directory and file name to the trace that it's generated for this particular method. So we can go into that handler and we can actually modify it to make the trace appear differently or get different information out of it. So here's the top half of that particular handler file. In the handler, we'll have an onEnter function. And if I had the bottom of the file, we'd also have an onLeave function. So onEnter is called just before the actual method is called, and onLeave is called after the method has returned. So you can see, and this is by default what Frida is giving me. It gives me a nice log line where it has broken out my specific method call interspersed with the arguments that were passed into that method. So this is exactly what we would want to modify if we want to see some different output. Now, when we modify handlers for Objective-C specifically, we can lean on Frida's JavaScript API to parse these arguments and get something more interesting out of them. Specifically, the objc.object function in the Frida API will create a JavaScript binding to the object that we specify. And what that will do is allow us to interact with that object from within JavaScript. If it's an Objective-C object, we can then call methods on that object, or extract more information out of it. So all we really have to do to get something readable here is just wrap our argument, args2 here, with objc.object. And since it's now a JavaScript representation, we can just use toString to see if we have something, a string description, something more human readable that will allow us to understand exactly what's going on here. So let's see how that new and improved trace would look. So here, we've got the exact same invocation, same command line, but it's now loading our modified handler. And lo and behold, we do have URLs, actual URL strings that we can see in the init with URL call. So at this point, we already, just from 2 iterations of tracing and a little bit of modification within our handler, we now have quite a bit more information than we started out with. And if our issue is that we can't get at this traffic any other way, we're now on our way to creating some insight into what that traffic looks like without ever even having to touch a proxy. So if you've never used Frida before, you're probably thinking that was really cool. I like all the pretty colors and all the information. I have no idea where that code was running. I have no idea what's going on. And that's kind of how I felt when I first started using Frida a few years ago. I had a hard time wrapping my head around where the different pieces of code were executing and why I could do certain things in some parts of code, but not others. So I wanted to really drive home, before we get into more examples, how this looks in terms of code execution. So there's 2 parts to what we were just looking at. There's a client script, and that's your script that's, something like Frida trace, that's something you've written in Python or, in Swift or something. That's actually executing on your host computer. And then there's the injective JavaScript, which is executing within the context of your application on your device. Now, the reason that this is important is you can also create client scripts in something like JavaScript, and it's easy to get confused as to where that JavaScript is going. So just keep in mind that there's 2 components. So what we just saw with the handlers and Frida trace is running on, for instance, my laptop, while the handler that we modified is executing on the device. So as we look at different examples, try to keep that distinction in mind, because it is important that, for instance, if you want to output something to a file on your computer, you're not going to be able to get there directly by the code in your handler. You're going to have to do that in your client code. Okay, so how can we use Frida? Well, we've already seen that we can monitor method input and output at runtime and, tweak exactly what we're getting in, for instance, the Frida trace output. But when we're looking at a specific application and we don't want a one size fits all solution, we can also craft things that will analyze data or functionality specific to that application. We can also use it in a more generic way to bypass controls like SSL pinning, or jailbreak or root detection, or even manipulate the application behavior. So, for instance, the things that we have to repeatedly click on in the application, we might actually be able to automate that process through some Frida scripts. But one of the first things you'll probably use Frida for is simply exploring what an application looks like and how it behaves under the hood. All of that functionality and behavior that's not immediately accessible to you, either through source code or through interacting with the UI. So let's take an Android example. I want to really enumerate all of the things you can get out of Frida trace, because that's probably one of the first places that you would start using Frida. And besides tracing Objective-C functions and methods, we can also trace native functions as well. So -I, we can use that to apply a pattern to find functions in a very similar fashion to the way we use -M for Objective-C. And we can also use -I, and that will hook all the functions in a library that matches the pattern that we specify. So at the bottom, I have a command for Frida trace that targets the Google Photos app on an Android device. And my hypothesis here was, I'm kind of curious what kind of database activity occurs within this application. And I don't just want to know like SQLite calls, so that's really critical. I want to know where those databases are. I want to know the path to them so that I can go investigate them on the file system. So in this case, I've specified -I open in the hopes that I'll get some file open commands. And then I've done the capital I for SQLite because I'll be honest, I can never remember library names. So I always have to use asterisks to just match based on the functionality I want. So I want whatever library is going to contain the SQLite functionality. And just to give you an idea of how powerful this is, after I ran that and then looked at my handlers directory, this is just a portion of what I saw. So it found libsqlite, and it made a handler for every single function within libsqlite, which is quite a lot of functionality. So this is really powerful if you know that an application uses a library, you're not sure what parts of the library it uses, or maybe it's a library that's not well documented or completely undocumented, so you don't even know what's in there. And you really just want a quick look at, via tracing, at what the application is doing with it. So this will dump everything and give you the option to modify any of these handlers and utilize them in Frida Trace. So once I actually execute that trace command against the Photos app, here's a couple of excerpts of what I saw. So in that top screenshot, you can see immediately we have a bunch of SQLite calls. And remember how I talked about within a thread in the trace, it will show us how those calls are nested. And that's exactly what we're seeing here. SQLite 3 OpenV2 is called, and then from there we can see a bunch of other calls that, that are executed after that and kind of how those are ordered. And among that, I've highlighted that we do indeed have an open call. So we can see exactly where that database is on the file system. And if we're interested, we could go, if we have access on that device, we could go and grab it and see what's contained there. But we also can tell that this particular database is what all of these SQLite calls are acting on. In the second screenshot, we see we have a SQLite 3 exec call. Now, unfortunately, with this particular library, we don't have any arguments being printed to the screen by default. So we would have to go into that handler and do a little work to try and parse out what the args are and interpret them so that they could be printed. But we do see here that since there's an exec call, there's probably a query string that we could print with just a little bit of work on that handler file. So what you can see from this is using a trace to explore when all you know is a kind of a high level idea of what you're looking for can be really powerful and pretty easy using Frida Trace. I want to take one more example using wildcards and combining a couple of the things that we just saw to look at the iOS keychain functionality in an application. So a lot of times iOS applications will want to store stuff in the keychain, but won't necessarily directly use the low-level keychain APIs because they can be a little complex. So they'll use some sort of wrapper class. Either they'll build their own or they'll use something off the shelf that wraps those calls, both for ease of use, but also sometimes because maybe they're applying a layer of encryption or some sort of transformation to the data before it hits the keychain. And it can be really helpful when you're looking at how an application uses the keychain to determine what those layers are. So here I'm introducing another flag, which is -F. And what -F does is tells Frida to actually launch the application itself instead of attaching to a running application. And this can be really key when you're looking at something like Keychain, where you expect that there's a good chance when that application launches, it's hitting the keychain right away if it's storing credentials there or tokens or something that it needs to authenticate. So we want to make sure that we're attaching very early so that we're getting all that information in our trace. So here we're using -M, and we've got a wildcard statement with eChain, just so that we'll get classes that match either a capital K or a lowercase k, because we just want any kind of generic keychain wrapper class. And then we're also asking it to trace just the function sec item copy matching, which would indicate that some keychain information is being retrieved from the iOS keychain. So let's see what this would look like. So if we execute this on DVIA, which is the Damn Vulnerable iOS app, and by the way, this is a great app if you just want to kind of explore what Frida can do in a safe way, and something that you can get source code to, this is a really good way to get started. So we're going to execute this on DVIA, and we'll see right off the bat, we get quite a few functions that it's instrumenting. It found a lot of keychain classes just with keychain in the name. In fact, it traced 720 functions. And this is actually not terribly unusual if your application is large and you have a pretty generic wildcard statement, you could get hundreds or perhaps even thousands of functions and have to try a couple times to whittle that down. In this case, after I started exercising the application, right away I got some traces from two particular classes, PD keychain bindings and PD keychain bindings controller, that look like maybe they're doing some interesting things. We can see that there is a value being set for a key path. We can see a service name, which might correspond to the service name used to get information in and out of the keychain. And indeed, we see sec item copy matching is being called. So we're in the right place and we're hitting the right functionality. And this is likely, if we're interested in keychain wrappers, this is likely where we want to be. So just looking at that trace, what did we find? Just to recap, we've got two classes that we think are pretty interesting that we want to explore some more. And we have at least a few areas where either we think keychain information is being stored or being retrieved. So we have a store string for key, we have a string for key, which might be retrieving information, and we have a service name, all of which are on PD keychain bindings controller. And we also know that sec item copy matching was called a couple of times. Now, at this point, if I'm looking at this trace, and this is my first iteration of tracing, my big question is, what is it putting in the keychain and what is it getting out of the keychain? And it's true that on iOS, if you have a jailbroken device, you can just dump the keychain outright and find it. But what I want to demonstrate here is that sometimes you can go from a trace and say, I want to get more information. And sure, I can modify that handler, right? I could modify my handler code to just print those return values, but it might actually be easier to just directly call the methods. If we've already seen how they're used and we know that we can invoke them with the right arguments, maybe we should just do that and see what data we can get back. So that's where the Frida command line interface comes in. The Frida CLI is a JavaScript REPL, and if you're not familiar with that terminology, that means read, execute, print, and loop. If you've ever used something like the Python command line interpreter or the Node one, that's pretty much what you're going to be working with. This will feel pretty familiar. So we can just type out JavaScript commands in the CLI, and those will be executed in the context of our application. We can also collect commands together in an agent script, just a whole file of JavaScript, and load that into the CLI, and it will inject it into our application at runtime. So this can be very handy when we just kind of want to explore and try some things, try invoking some methods within our application and see what happens. So I have a little video, and this is just going to show the same example, DVIA, some of the ways that we might be able to explore what we saw in the trace to get more information. So one of the things in the trace that I noticed was that there were some methods to get a shared instance of these two classes that we're interested in. This won't always be the case, but since it is the case here, I'm going to utilize that instead of trying to, allocate and init my own instance of these classes. I'm just going to use what the application already has available. So I'm just creating a variable called bindings here, and I'm using Frida's objc.classes, which is just an array of all of the loaded classes within the application, to grab a handle to PD keychain bindings and then call shared keychain bindings so that I get an instance, hopefully, of that class. And you can see that Frida is going to try and autocomplete where it thinks it knows what we want to do. And that includes things like autocompleting right here, the name of a method that hangs off of that particular class that I'm looking at. So now what I want to do is, this is another freebie from Frida. Let me see if I can just pause it right here. So one of the things Frida provides for us is the $own methods attribute, which is really cool because when we use this on a class that we've grabbed a handle to, it will tell us all of the methods that belong specifically to that class. So not inherited methods, just for that class. So we can dump this on a class of interest and see exactly what it's comprised of. And this can be really useful because, for instance, if I'm looking at this controller, I see, hey, it has a values method. So what happens if I try and just call values? Maybe it'll dump the actual keychain values that I'm interested in. So we can see, first it gives us a handle. So we're going to try and call toString. And indeed, we've just learned a big secret, that the application was protecting. So we don't know at this point if this is pulled live from the keychain or if it's cached, but it's something interesting that we're going to want to perhaps follow up on. So let's try calling string for key with that key, because this is something we saw in the trace. And what does it return? It returns big secret. So there's a good chance that what we saw in the trace when it was doing string for key, it really is hitting the keychain. And the data that we're getting back now is actually the keychain data that we're interested in. So this is a really great starting point for us if we're wanting to understand better how these keychain classes in this application work. Now, once you've played around in the CLI a bit and you've figured out a progression of commands or a progression of JavaScript that does something interesting in your application, you're probably not going to want to type it over and over again, because if you're anything like me, you hate typing, and I will do anything to not have to type as much as I do. So once you've tested it, you can bundle that into a single file that we refer to in Frida as an agent. And this is just a JavaScript file that you can load via the CLI, and it will inject it into your target. But one of the really cool things that I lean on a lot when I use Frida is that when you define functions within that agent, they basically appear within the CLI for you to call. So it's almost like creating new commands within your own little environment for application testing. So the way that we would load an agent is just with Frida-L and then the path to our agent and the name of our target. So let's think about a way that we might want to use this on a regular basis. So one of the downsides of Frida Trace is, as of yet, there's no support for matching Java methods the way that we can match on Objective-C methods. So if what you're targeting is a Java method, you're kind of on your own. There's a lot of tools and scripts out there that folks have created to sort of bridge this gap, but I think it's useful to see how to do it on your own manually so you can understand all the moving parts here. So when you want to do this, you have to replace the method implementation for the original method with something that we can use to log our own data to the console. And there's two key items in the Java API, which is similar to the OBJ-C API that we saw for iOS applications. And those are Java Perform and Java Use. Those are things that you're going to use quite a bit if you're targeting Android applications. So let's say that something that you're interested in looking at across all the Android applications that you test is their use of web views, because there can be some very interesting bugs that surface when applications use web views and they're not very careful about their implementation. So if we just want to see very simply what a web view is loading, maybe we want to trace the load URL method of Android WebKit WebView. And this code, this little piece of self-contained code, is just enough to do just that across any application that uses load URL. So let me walk through this line by line, because there's a lot of information here to absorb. So the first thing we're going to do is use java.available to just make sure that the Java VM is loaded, because we don't even want to bother with the rest of it if the Java VM is not loaded. It's kind of just a sanity check for us. And then we're going to move to using java.perform on a function that we've defined. Now, java.perform makes sure that the current thread is attached to the VM, and then it will run whatever function we specify. So we've put our code in this anonymous function that we're passing to java.perform. And the first thing we do there is grab a handle to a web view using java.use. And java.use just wraps the name that we pass to it. It's just going to wrap a JavaScript wrapper around that class so that we can utilize it throughout the rest of our JavaScript and interact with it. And once we have that handle that we've defined in const web view, we can do things like instantiate new instances of that class or call methods from it. So on that next line, what we're going to do is specify that what we're interested in is load URL, and we have to tell Frida specifically what flavor of load URL we want to manipulate. Because if you're familiar with Java, you know that you can have multiple methods with the same name that have different signatures. And so we have to be very specific here. We're going to use overload to say we want the version of load URL that takes one argument of type Java-lang string. So that way we're specifying just that particular method. And then we're going to replace the implementation by setting it to a function. And our function takes a URL, so same kind of signature as the original. And then all we're going to do is use console.log to log a pretty line with some color coding and everything with that URL that was originally passed in. And then we'll call finally the original implementation of the method using the .call method, or the .call function here. Now that was a lot of information. I highly encourage you to come back and revisit this slide in the video and walk through it line by line to make sure you understand if this is something that you're interested in. Because in a nutshell, this is a lot of the functionality that you will need to build your own kind of tracing capability within Frida. So let's see what that looks like if we execute it. Here I am loading this into the Amazon Shopping app. I only picked this example because honestly, I went through a bunch of apps and this was the first one that had some interesting output. And what we're seeing here is we have our nice color-coded input, and each of these lines represents a URL that was loaded into the web view. Now, what might surprise you about this is we're not just getting your typical HTTP, HTTPS URLs, we're also getting JavaScript. So if you have an application you know is JavaScript heavy, or maybe you suspect it's JavaScript heavy and you know it uses web views, this is a great way to get a snapshot of that functionality that's executing in the web view. And if you look through this trace, I mean, just from looking at this and not even looking at the application, you can definitely make some conclusions about, the platforms that are running within this application, the frameworks that they're using, some versions, and make some educated guesses about what's going on in that web view. So this is pretty powerful for such a small amount of code that we've leveraged here. So there's a couple of different use cases for agents besides what I've just shown you, which is basically, that automating of something tedious, or, gathering something that you might want to use across a lot of applications. We also want to think about the fact that we can use an agent to define new commands for the CLI as well. So I want to show a couple of examples of more complex programs that are fully contained in an agent, just to kind of give you an idea of what is possible in your own programs. So first of all, I want to talk about a tool called BlueCrawl. BlueCrawl was written by a colleague of mine, Keith McCann, over at IOActive, and you can get the full source of this from our IOActive GitHub repository under BlueCrawl. BlueCrawl is a Bluetooth metadata collector, so it will collect metadata from a specific Android device, and it leverages the Frida CLI to be able to very easily inject it. So you just load this up into your device, and you don't even really have to interact with it. It will kind of do all of the work for you. And I like to point people to this if they're interested in writing agents for Android, because it's very nicely laid out, very organized, and very well commented code. And I want to point out a couple of specific highlights within the code, just for some features that I think that you will need if you're going to write a lot of scripts for Android applications. First of all is java.enumerate loaded classes. And enumerate loaded classes basically just goes through and enumerates all of the classes that are loaded currently. And in this instance, it will take a callback object, which is what is specified between the curly braces here and here. And that will have two functions defined, an onMatch function and an onComplete function. The onMatch function will be called for the name of each class that is found. So in this case, what we can see Keith is doing here is he's splitting the class name on just a dot and looking to see if the second name is Bluetooth. So something like com.bluetooth, android.bluetooth is going to match on this. And for those matches, he's just going to log what the name of that class is. So this is a simple way to get a log of everything that's loaded that matches a specific pattern. Now, in this case, we don't have anything in the onComplete function. OnComplete is going to run after we're done enumerating everything. So this is a good place to do any wrap-up analysis or just output something in the log to indicate that we're finished with this portion of the code. The second thing that I want to highlight is java.choose. And this is also an enumerator. It works kind of similarly to what we just saw, but instead of enumerating classes, we're enumerating instances. So Frida is actually scanning the Java heap here to find instances of a class that match a class name that we've passed it. In this case, we're looking at android.bluetooth.bluetooth.get-server. And for each instance on the heap that Frida finds, it's going to pass that to our onMatch function. So here, we can take that instance and do maybe some more analysis on it, which is what's occurring here. We're going to call a specific method on it so that we can crunch some more data and output some more log lines on it. And then we do have an onComplete function here. So after we're finished enumerating all those instances, we're just going to output a log line to indicate that we're done. So what this looks like once you run this, and I ran this on my Motorola Moto G5 Plus, what we can see is, first of all, in that first screenshot, it's enumerating all of those loaded Bluetooth classes that it found on my device. And then in those second two screenshots, what we can see is these are instances where java.choose was used, and Frida found some specific instances of the class specified, and we processed it and we printed that out to the screen. And this is only a portion of the information that BlueCrawl outputs. I'd highly encourage you, if you have a handy Android device, to try this yourself, and you'll be able to see just how powerful it is and how quickly you can gather an awful lot of information and crunch that data and return it to the user. And this would be extremely useful if your target was an application that makes heavy use of Bluetooth. So for my second example, I want to talk about a program that defines some functions that are used as commands in the CLI. And that's a URL scheme fuzzer that I wrote as a POC for iOS. Just for some background for those who may not be as familiar with iOS, one of the ways that iOS applications can share data is through a URL-based data sharing mechanism known as custom URL schemes. And the way this works is an application can register a scheme. For instance, a scheme might look like my app. That would be the prefix on a URL. They can register themselves as a handler for that scheme. And then when any other process loads a URL that starts with, for instance, my app : // the application that registered it would be launched or foregrounded and handed that URL to handle and take action on further. Now, the problem that I see a lot with these custom URLs is applications many times will neglect to fully validate the input that's coming in via that URL. So they're parsing parameters out of it or doing something based on the path that's in that URL, and they forget to make sure it's not null, or they forget to make sure that what they think is an integer is actually an integer. And so fuzzing can be a really easy way to surface bugs in that handling, because frequently, if they're not validating that input, malicious input will just absolutely crash the app cold. So I wrote this little fuzzer to show that this is something that we can actually execute from within Frida and manage the whole process without having to have any manual interaction with the fuzzing. So this is an example from within that agent.js that I wrote of a function called openURL that I wrote. And you can see from the second screenshot that once it's loaded in the CLI, it will auto-complete that openURL as if it's any other command or any other, Objective-C method that we're handling within the CLI. So this is an easy way to add some functionality that's specific to, for instance, some iOS testing that I might want to do. I can just bundle that all in an agent that I load, and voila, I have some new functionality that's available to me in the CLI. Another highlight in the URL scheme fuzzer, and I'm not going to go over the entire thing, but I do want to note, I mentioned automating UI interactions to make it easier to perform certain functionality that's more automated. And here I've got an example of that where I defined something called home single press. Within my fuzz process, one thing I wanted to do is, as soon as the application loaded one of these URLs, I wanted to make sure that I backgrounded it before loading the next one. So I kind of got a clean load where it was foregrounded every time. And I didn't want to sit there and click the button, because that would sort of defeat the purpose of the automation in the first place. So with home single press, what I did is just detected what version of iOS I was dealing with. And then I leaned on an Objective-C class called SBUI controller, which has a method that is called when you physically click that hardware button. So I'm just calling the corresponding function as if I had clicked the button. And to iOS, it thinks the button was clicked, and it will behave that way in background, the application. One thing I do want to point out here as well is I'm using something called objc.schedule. And what that's doing, you can see I'm wrapping my one line of code in a function that I'm passing to objc.schedule. That's because I want to ensure that it runs on the main queue. So using this, we can specify what Grand Central Dispatch, if you're familiar with iOS coding, we can specify what queue it uses. I can ensure it's the main queue, but also I get some free memory management along with that. And a little bit later, I'll point out how if you don't want to use objc.schedule, how you can do that memory management, just to ensure that you don't run into any issues in your JavaScript. All right, so let's see what this looks like. Oops, maybe not. Try that again. Let's see what this looks like in person. So here I'm going to load my fuzz script right here, my fuzz command on Etsy, because Etsy uses URL schemes for deep linking. So I've selected a particular URL that's supposed to point me at a listing, and I've got a placeholder, this 0 in brackets, that is just going to be replaced by my fuzzer with a list of potentially malicious inputs. And I'm going to check for a crash each time. But what I want to point out here is you can see, like, this is hands-free. I can walk away and get a cup of coffee and then come back and see if it found anything, because it's completely doing the backgrounding of the application without me even having to touch the device itself. So this is pretty handy, and just kind of an example of, if you do have a sort of a physically labor intensive area of the application where you know there's going to be clicking, if you can figure out how to do that using either the environment, the way I'm using some SBUI controller methods, or using the application itself, you can save yourself a little bit of work and effort there. Now, the script I just showed you is posted out on the Frida Codeshare site, so you can actually try this out yourself and see it live. Frida Codeshare was created for the express purpose of giving the community a way to very easily pass along different code snippets and demonstrate different techniques. And one of the great things is you will also see a lot of projects improved upon in Codeshare. In fact, I think there's at least 1 or 2 people who have forked the URL scheme fuzzer with different add-ons and improvements. So you get a lot of perspectives into the same kinds of code and figure out a lot of different ways to approach the same problems. So I want to show directly an example of using Codeshare and how easy it is to load some of this code in and try it out without having to really muck about in the internals of the code. So when you use the -- Codeshare flag within Frida, the script is actually downloaded for you. And the first time through, it will ask you to approve it. It will take a hash of it so that the next time you use it, if it's changed, it can notify you and you can go out and check out those changes and make sure that you're okay with them before you use them in your testing. And all you have to do is pass along the path on Frida's Codeshare site to the specific script that you want. So to load the URL scheme fuzzing script, this is what I would use as my command line. But let's talk about one other really simple Codeshare script that I know I use quite a bit and I think is very handy, and that's to bypass SSL pinning on iOS. Now, for some background, mobile devices can be made to trust an arbitrary certificate authority as if it's a root certificate authority, simply by, for instance, downloading a certificate on the device and explicitly trusting it, or sometimes installing a profile to the device and trusting it. And in this fashion, this can enable man-in-the-middle weaknesses if that certificate is malicious and somebody can eavesdrop on that traffic, subsequently using that certificate. We all know, though, even without that use case, SSL and TLS vulnerabilities do happen. And some of them also enable fraudulent certificates that may be trusted as if they are not, in fact, fraudulent. So mobile apps have a way to mitigate the risk from some of these issues by pinning known good certificates. So as the mobile application, if I know what the certificate from my specific backend API should look like, whenever I contact that backend, I can compare it to what I know about the certificate. And if there's a mismatch, I can just refuse to connect. Now, this is great for mobile application security, but it's really kind of annoying for mobile application security testers because it makes proxying more difficult. It's one more hurdle that we have to try and scale before we can really proxy the application and analyze it. And so having a quick way to bypass this is really crucial. On iOS, bypassing SSL pinning can be performed by intercepting the calls at a low level that perform that certificate validation. And those are going to vary depending on the iOS version. But on iOS 11, in this example, we want to target a function called NWTLS create peer trust. And it's nice that there's really only one function that we have to intercept and short circuit in order to bypass this. To do this, we can use the interceptor API in Frida. And there's 2 main ways we can do that. One is via attach, where we define an on-enter and on-leave callback. And if you're thinking, this looks really familiar, where did I see this before? It's because that was one of the first examples we looked at with Frida trace. And Frida trace uses those same on enter and on leave callbacks, but for the simplicity of it, they don't really tell you that you're using interceptor at the time, even though that's what's going on under the hood. So you already used it and you didn't even know it. The second way that we can use the interceptor is via replace, and that's what we're going to want to do when we're short-circuiting a function or a method in order to do something like what we're doing here with bypassing SSL pinning. So before we can really replace a method, we have to be able to find it first. And to do that, we can use module.findExport by name. This is going to return an address that we can then use. We can wrap it in a native function and use that to later on replace it in the interceptor. So this little snippet of code below is just us in creating a variable called TLS helper create peer trust, and we're using that to create a new native function. And the first argument to that native function is going to be the address of the function. So we're using module find export by name to find that address. And all we have to do is tell it the name of the function we want to find. And in this case, the name of the function is pretty unique. I'm not worried about it being found in multiple places. So I don't even bother to tell it that it's in a particular library, but that is something that we can do. We can specify where that function will be found, or we can pass null if we think there's only going to be one instance of it. And then for our native function definition, we're telling it, first of all, it returns an int, and it takes 3 arguments that are a pointer, a bool, and a pointer. And that way our native function will mirror the actual definition of the function that we're pointing to. So now we want to replace it, and we'll use interceptor.replace to do that. It takes 2 arguments. The first is that target that we just created, that pointer to our original function. And then we're going to create a native callback as the replacement. And the native callback is just a wrapper around the JavaScript function that we want to replace it. And it's going to look kind of similar, the way it's constructed, to the native function that we just created. So this is the bulk of our SSL bypass. It's very short and simple. We're going to use interceptor.replace. We're going to pass it the handle that points to our original function that we want to replace. And then we're creating this native callback. We're passing it the JavaScript function that we want to use as the replacement. And that's really just one line. We're just returning an error code that indicates success. So when iOS gets this return code, it's going to say, oh, everything's fine, nothing to see here, we're all good. And that's exactly what we want to happen. And then we're also telling our callback that our function returns an int and takes a pointer, bool, and pointer, which correspond to these 3 arguments. So it's going to have the same signature as our original function. And then we're just logging a quick message so that we know our script is working. Now, this is something you can try for yourself as well out on Frida Codeshare. Even though it says iOS 10 SSL bypass, it will work both on 10 and 11. I've been kind of adding code to it so that it's compatible with additional versions. And the nice thing is, not only will you, if you go to this URL, you'll get the full source code, but you will also get a hint as to how to run it on your specific application. So there's no guesswork here. So let's real quick just look at how this works. So here I'm proxying my device, and I've loaded the App Store, and the App Store is not being cooperative. It does not want to use that proxy because it knows that it's not the right backend. So I'm just going to invoke my SSL bypass and refresh, and just like that, now I can get through my proxy. It will send the traffic very happily and think that everything is just fine. So that's a pretty great output for just a small amount of code. And I can use this on pretty much any application for iOS 11 that is attempting to use certificate pinning. And I'll be honest, I don't think I've ever hit one yet where it has not worked. Oops. All right, I have one more thing I want to talk about with our last few remaining minutes, and that's writing standalone tools. So far, everything we've looked at has used either Frida Trace or the Frida CLI for an assist. And there are times when that's just not going to be enough. That's not going to be a good fit for the use case. One example is if you have a non-interactive tool, you could load it in the CLI if it's completely contained within JavaScript, but you don't really need to because, again, you're not interacting with it and the CLI is interactive, so it's not necessary. But there also might be more complex needs that you need to address. You might want to analyze some data coming from your JavaScript that's running on your device, and then write some of that out to a file on your host computer on your laptop. That's not something that's easy to address using the Frida CLI out of the box. You also might want to pipe some input from another process. For instance, maybe you want to run a fuzzer to generate some data, or something like maybe Redomsa to generate some data that then you pipe into the JavaScript that is running on your device to perform some kind of fuzzing function. And again, that's not really something that the CLI is set up to address. So this is where you might want to write your own standalone tool. And just to recap, you can do this in Python, you can do it in Node, you can do it in Swift, you can do it in .NET. There's all of these language bindings supported so that you can pick the one that you're most comfortable with to write your tool. Now, there's some elements of a standalone tool you have to think about that you don't when you're using the CLI because they're kind of taken care of for you. For instance, when you're writing your own tool, you have to attach to the process yourself. You have to take care of injecting the script and sending information to and from the script from your client. And these are things that you don't really have to worry much about when you're just using Frida Trace or the CLI. But it's not terribly difficult to do that. And I'm going to show an example of doing some of this just with Python. So if you want to attach to Frida over USB, you can just use frida.getUSBdevice.attach and pass the name of your process to it. That will give you back a session. That session can then be used to create your script using a source of your script, basically just the JavaScript string that comprises your script, and then use that script object that's returned to create a message handler for any data that's coming back from the script to your client. And then use script.load to load it and inject it into your process. So that's not too much code. It's fairly straightforward and simple. But what if you want to call some specific functionality from your client script that resides in the JavaScript that's injected in your device? Well, for this, Frida provides rpc.exports. So in my JavaScript, if there's some functionality that I want to expose to my client, I can use rpc.exports and then define a function name and set my function definition to that. And then in my Python script, I can call that using script. That's that script handle that we had just received back, script.exports. Whatever my function name is, and then pass my input. So this is enabling some of that bidirectional communication, but also enabling us to invoke specific functionality in our client whenever we want to. So this is sort of a work in process that I've been working on in my spare time, and that's an iOS class dumper. On iOS, the Objective-C runtime has quite a bit of information, and Frida provides some of that to us for free by letting us see the list of Objective-C classes that are loaded and some of the attributes of that. But I wanted to try and get something a little more complex that mirrors some of the class dumpers that are available from other providers. So I decided to see if I could do this using Frida. So within the script, I have just a classdump.js that does a lot of the on-device functionality. And I just read that script in, create my script, and then I have a message handler that I kind of wanted to show you so you can see what the message handler can look like. My message handler is just a function that looks at, first of all, what type of message is it that I'm receiving from my embedded JavaScript. So if it's a type of send, I know I want to look at it. And then I check the payload. If the payload is a dictionary, then I can be pretty certain that it's something that my script created that I need to further process. And then I'll open a file. This is a file that's written to, for instance, my laptop, my local computer. And I will name it first. The directory will be named after my application process name. And then I'll have a class name embedded in my payload that I'll use to create the file name. And then I'll just write the contents of the payload dump to that particular file. And that's really the bulk of what the Python client has to do. But what about the JavaScript? Now, this is not the whole class dump. It's pretty long. I didn't want to bore you with all the details of that. But this is the functionality, the rpc.exports functionality that I am exposing to my Python. It's called dump bundle. Now, remember, I talked before about objc.schedule and how it does some free memory management for us when we use it. I'm not using that here, so I need to do that memory management piece manually. So whenever you do Objective-C work in Frida and you're not scheduling it, you definitely want to create an auto-release pool and alloc init it at the beginning of your function. And then I use a finally block here to release it at the end. And that's just making sure that that all that memory management stuff is straight and that I'm not going to encounter any issues because I'm lacking those 2 lines of code. And then the block here, I'm leaning on the objc.classes that Frida provides to iterate all through the different class names that are available and then see if they are in the main bundle for my application or not, because I only want to dump what's in the main bundle and not all the other loaded frameworks and libraries. And then I'll just pass it to another function dump class that will analyze and gather all the data from that class that I need. But what I want to point out here is that within this function, I'm calling send. And send is what is constructing that JSON object that is serialized and sent out to my Python client that contains my class name and all of the information that I've dumped. So if I execute the script against DVIA, I have a nice message that is printed to the console telling me what class I've dumped. And then afterwards, I can check that DVI folder that was created by the script, and I can see all the header files that were generated by my script. So this is just a nice example of what you can do with a standalone script, some of the functionality that, that you can take beyond what the CLI can do for you. And you're still building on top of Frida. You still get all of that free information that Frida provides, but now you can customize some of the output and some of the functionality that occurs on your host computer a little more closely. All right, so I hope that I have given you just enough information to be dangerous, and I hope that you want to learn more about Frida. If you do, please do visit their website at frida.re, and highly recommend visiting the Codeshare site and trying out some of the examples there and looking through some of the code to get an idea of what you can do with Frida. I also would say if you're new to Frida, head out to the awesome Frida repository on GitHub, because this has not only some code samples and pointers, but lots of blog posts, video walkthroughs, and talks that have been given on Frida. And this will give you just a great idea of what the possibilities are using Frida in your own bug hunting work. So thank you very much. I think we have a couple of minutes maybe for questions. We'll see what pops up.
Holy moly, that was an awesome talk. Thanks, John.
Thank you.
That was amazing. I remember when we were doing the mobile stuff that a lot of those things were problematic because the tool set was so diverse and spread out, and gluing it together on the command line of the broken device, and it wasn't iterative at all. So it fixes a lot of those problems to have the Frida tool wrap all that around, and you can make your own custom functions and stuff like that.
Yeah, absolutely. And I've replaced, honestly, a lot of those little standalone command line tools with equivalent functionality from Frida for that very reason.
Very cool.
Yeah, you did a great job. Everyone in chat is a big fan, to say the least.
Oh, thank you.
Any questions out there?
I know I've blasted a fire hose of information at everyone, so they may be just stunned, trying to absorb all of it.
We'll give it a little bit. There's like a 20-30 second delay. So we'll see if anyone comes in with a question. But we might be good to go because we're winding down on the hour. And we'll have our next speaker in about a minute or so. So it looks like you did a great job filling up the time, and with your content was awesome. Thank you so much.
Yeah, and I'll just say if anybody thinks of questions later, you can absolutely hit me up on Twitter. I am at Dawn Isabel. It's just my name all smushed together. So I'm pretty easy to find, and I'd absolutely love to answer your questions if you think of anything after the fact.
Yeah, with the Bug Crowd Twitter account tweeted out your Twitter handle at the beginning of your talk. So if you're watching this and looking for her Twitter handle, just check the Bug Crowd Twitter. All right, well, thank you so much, Dawn. I appreciate it.
Thank you.
Flip over and we can